Nice. Right, so I was going to give you a gentle and brief introduction to Cangjie, but then I sort of changed my mind. So this is what I'm going to talk about. Towards say concurrency in Cangjie and a little bit of Cangjie so that you don't think I scammed you guys here thinking you are going to learn all about Cangjie. So first things first, 3 slides about Cangjie. I'm just pretending you guys don't know Cangjie at all. So Cangjie is the name of this four-eyed dude who allegedly invented the Chinese characters. And the most important thing here is that it's pronounced as Cangjie with a little bit of the TS sound. Definitely not Cangjie, so please don't mispronounce it. And then a little bit of Cangjie it is fully developed by Huawei. General purpose, high-level expressive, statically typed, memory safe, garbage collected language, and we are natively compiled using LLVM backend onto Linux, macOS, Windows, and most importantly, of course, Harmony OS, which is going to be the de facto OS on Huawei devices. So here's a sort of a list of the features that we have. Well, this is not all the features that we have, but like these are compared to other languages. You can see all the blue text here that we have all of them. And Magnus is going to talk about if I handle this, supposedly. If he didn't change his mind to talk about something else. Right, so this is what I really want to talk to you about towards safe concurrency in Cangjie. It's more sort of like a story of what we're trying to do and where are we going to. So what is safe concurrency and why do we care? So safe concurrency is basically what you want to eliminate data race in your program. So this is a ChatGPT/wiki definition of data race. So data race happens when 2 or more threads access the same shared resources simultaneously. Data race is bad, we all know that, right? Like it leads to a defined behavior, it might crash your program, or even worse, it gives you trash values that you think the program works, but it actually didn't. And they are notoriously difficult to debug. But why do you care? Well, because every UI application is inherently concurrent. So this is a typical UI applications. You have the UI thread running. Inside the loop, you're basically an event loop, right? Like you have events coming in, you process the events, and while you're processing the events, most likely you would spawn some background threads to do some heavy computation. And inside this background thread, most likely you have to modify the UI states. For instance, you want to modify, you want to update the text in a text box. But then the UI thread continues to draw the components. So in this step and this step, you basically would have data race if you are not being careful with it. And the common practice is basically to tell the developers, well, you should be careful. You should only update the UI states inside the UI thread, not in this thread. For instance, in Kotlin, there is a framework, Jetpack Compose, which is a comprehensive UI framework, declarative, all that stuff. So not sure if you can see with the banner there, but there is the composable macros. So this is basically a definition of what a button is. Well, a custom button. So inside this custom button, I have some states, internal states of this button. And then when the button is clicked, I basically spawn a coroutine to do some long computation. And then in this coroutine, I update some states. And this text box is basically showing you the value of the count states. And by using this, you run into data races because this spawn the coroutines not on the UI thread, but on some, well, you don't know which thread it is. It spawns a coroutine anyways. So it's very easy to write the wrong thing. So that's the wrong thing. So what you have to do is that after you spawn a coroutine, you do some long computation, and then what you have to do is that you have to spawn the coroutine on the main thread. The main thread is the UI thread, by the way. And inside this coroutine, then you update the states. And this segment of code will be run on the UI thread instead of the background thread. So this is what you have to do in order to make it safe. And of course, as language designers or language developers, we always look for things that that can improve your language so that the developer don't have to be careful themselves. The language will help them to write the correct programs. And this is what we want to do. So what we want is basically to statically guarantee data race freedom. And in order to talk about this, we cannot avoid talking about Rust. So I'm not going to show you any Rust program here. The Rust approach is basically following that principle. Either you have mutability or you have aliasing. They cannot mix. So this ensures that you can either have multiple immutable references, so you can read all of these references safely, or you can only have one mutable reference of the same data at a time. And by construction, then you cannot have data race using the save part of the Rust. And if you want to really share data between threads, then you can use these primitives in Rust. You have atomics, you still have mutex, you have channels, etc. So the problem with Rust is that some would say that it's very difficult to learn Rust. Lifetime parameters might be cumbersome to write. And I know these are very, very, very subjective arguments, so that I grayed out. And if you know, Federico would object to this like heavily. But I would hope you agree is that Cangjie is a very different kind of language. Cangjie is more towards application, while Rust is more towards system language. And our user base are more familiar with Java, Swift, etc. So telling them to learn Rust is kind of more of a difficult step. And also having these kind of Rust full style ownership types in Cangjie would probably need a complete redesign of the language. You might as well develop a new language, or you might as well just use Rust. And then there's also the Swift approach. So Swift 6.0 also guarantees data race freedom. So in Swift, they use what they call isolation domains and sendable types. So isolation domain is basically just an actor. You can think of it as it's a container. Inside it, you have some internal states, and then each isolation domains communicate with each other via asynchronous method calls, like message parsing. So they don't share any states at all. For instance, in Swift, you have this declaration, which declares an actor. So you can have some member fields, and this is by default isolated to this actor instance. The function as well, this asynchronous function is also isolated to this actor instance. So inside the same isolation domain, you can access the member fields safely. So here you can change the value of balance, or you can read it safely. But then outside of the domain, for instance, I have here a top level asynchronous function. Then this is by default not isolated to any isolation domain, right? So what I'm doing here is I try to access the member fields of an actor, and then the compiler basically tells you that you cannot do it. It ends up in a compiler error. So the right thing to do it is say that you have to call this function or access these member fields asynchronously using a single wait, and now this is okay. But that is not enough to guarantee full data race safety in your program. For instance, you can imagine like if reference types can be passed into the async functions, and then it can be assigned to the members of the actors, then you're still creating aliases. The same thing with global variables capturing inside the asynchronous function of an actor. So what they do is that they basically say, oh, well, we just don't allow you to send mutable references to these asynchronous methods. And what they do is they created these sendable types. Basically, you can think of them as these types are passed. It doesn't matter if it's passed by reference or if it's passed by copy. Basically, anything that is immutable. Yeah, so only sendable types can be passed into or returned from these asynchronous function. For instance, we have the same actor here. Well, not exactly the same, but so we have some class type structure. So data is class type is a reference type. We have some asynchronous function receiving a reference type as an argument. And in here, when we're trying to send the data to the asynchronous function, then you get compiler error because the data lives in a different domain than the actor itself. So the same thing happens to global variables. Basically, the solution is that all global variables must now be immutable and of sendable type. So the problem with the Swift approach is that then it's not backward compatible because you cannot write global mutable variables anymore. All of the global variables has to be immutable and of sendable types. And there is also some problem with, because I skip a little bit, basically all the domains are static. So when you declare a functions, asynchronous function, or when you declare any members, fields, or variables, anything of that, you have a static domains. And the problem is that then it reduces code reusability. For instance, in this example, you have a data struct, which is a sendable type. So it should be safely passed between domains, right? But because the async function of this data structure is by default non-isolated. Even if in the actor, you have isolated member fields, and if you try to call this async function within the actor domain, you actually cannot do it because this async function is still non-isolated, and you're trying to call a functions from a different domain, or passing a data from a different domain. But passing a data to a function that is on a different domain. So my personal opinion on this is that I think they have mistaken something, and they should borrow ideas from some object encapsulation ownership type thingy, regional type thingy, and they could make this polymorphic, but yeah. So what we really want is that we want to statically guarantee data race freedom of only active states. We don't really need to guarantee data race freedom of your whole program. We don't want that. And also we want backward compatibility, basically. And that's bringing us to the OxCaml paper. So I'm not going to really dive into this paper, but basically they are working on OxCaml, but then they also want to retrofit some modes into OxCaml so that you can do more stuff to guarantee, for instance, to do manual memory management or to guarantee data race freedom as well. And they have divided all these modes for you to do it. So I'm just going to go through this small example here to give you a flavor of how what it does. So for instance, when you declare a global variable, you can say that it is a global variable by using some annotations. And then you can define the functions that takes in a local t. So local here really means that the lifetime of this variable should not escape this function. And basically this function, if you go into assign, so this is the function parameters. Yeah, okay. So when you assign x into this global variable, you're trying to assign a local thing into a global thing. And here you get compile time error. But the nice things of this is that it is backward compatible because you have all these default modes which still work with normal OxCaml. And as a bonus, you get memory management uniqueness under the same framework. But of course, data race doesn't come for free. So you still have to use these modes in order to guarantee data race freedom. So again, I'm not going to talk more about this. If you're interested, go talk to Federico or talk to Sam. So what we really want to do is kind of combining modes and actor. So if you don't know, we have an actor framework or actor library in Cangjie, which looks very similar to what Swift does anyways. So you have a class, you have an annotation actor, which makes these into an actor, and you have this receiver annotation to make these as asynchronous methods, basically what Swift has. And in here, when you call a receiver, then it returns you a future, which is like a promise, storing the pending result of this function call or asynchronous function call. And then when you call the get function of the future, then you block the current thread and wait until the result is back. So we have this in place already. So what we want to do is that we have the modes and the type system, the model type system to guarantee data race freedom for you. And then the next things we want to do is to use the actor framework to impose this usage of modes so that we could achieve data race freedom of the actor's internal states. This is still an ongoing project. I'm not saying this is the final thing, and I'm not sure if this works as well. Everything is still under development. So for instance, what we could do is that, for instance, you have some private internal states here, which is a reference type, and we can enforce that all the receiver has to receive a local mode of this class, right? So this object here has to be local so that it doesn't escape. And because modes are deep, these are going to be local inside this function as well. And in order to mimic the sendable type thing, right, in Swift, basically what we want to say is that anything you send to the asynchronous method has to be unique so that they don't have any aliases before you actually pass it to this function, so that they are going to be safe. If you, for instance, assign this argument to your references, then everything is fine. So back to what I talked about UI in the very, very beginning. What we envision is that every component is basically a special actor in which all of the receivers are executed on the same UI thread. For instance, what we could do is that all of the components are now actors, but spawn on the UI thread. And when you try to use it, you can create a button, and then inside the onExpect function, for instance, you can spawn some thread to do some long computation. And then what you could do is that you execute these receivers, and they would do the right thing safely. But this is going to be a huge modification to the existing UI framework. So I don't know. This is going to be a faraway trip. Not sure if I have time. Anyways, this is just one slide to tell you that we have distributed actors as well. So this will be public soon. Basically, you could define some actor interface, which is distributed. Well, not the interface is distributed, but you can export these actors to your cluster. You can have actors implementing this interface, and then you create a cluster, and then you say, in the cluster, I want to spawn this actor with some name and then pass in some arguments, and voila. You can use distributed actors as if they are local actors. And I think this is the last thing I want to talk about. Thank you very much.